We have a communication from the Department of Chemical Engineering at Amherst. The title is Solid-State Catalyst Transformations During Oxidation Reaction over Vanadium Oxide. And the communication will be presented by Curt Conner.
Thank you very much. I guess I'll get this going here. We've heard a lot of different pictures of what happens over vanadium. And I'm going to try to tell you the picture of what happens from the solid state up. So we are going to talk about solid state transformations during this. It's a multimedia presentation, so I'll be going over the slides fairly quickly. The co-authors are Mike Harold, who's currently at DuPont, and Dave Sullivan, who's working with, has a good job now. Dave did all the work. I must first briefly talk about and remind you that vanadium is a very active oxidation catalyst for a lot of different oxidations. What we try to do is actually study vanadium in situ, and we're not looking at supported vanadium. This is pure vanadium. I'll look at the reduction. When I talk about reduction, I'm going to talk not just about the surface, but we'll see the whole bulk becomes reduced, and reoxidation. And then we'll relate this to some work using NO and NH3. I'd like you to pay attention to the rate controlling step in this process and the mechanism. And by mechanism, I'm going to talk about the mechanism where instead of using S and M to indicate solid states, I'm going to talk to you about various forms of vanadium and what they look like and what we can do with that. The work was supported by the Department of Energy, Basic Energy Sciences section, and they contribute the finances behind this. So we'll start out at the top here, talk a little bit about vanadium, and I'll show you a little bit about a new technique, emission infrared, to enable us to find out what's going on in the solid state. Now what I'm going to do is try turning this off. Can't get too far, can you? Just short enough. I just take this. Okay. Press power and power forward. And then we turn some lights off up here. And there's the light that's using on the back room, yeah. Okay, most of you are, all of you are familiar with a variety of different reactions that are done commercially using vanadium as a catalyst. Everything from sulfuric acid to maleic anhydride. And more recently, in talks we've seen at this symposium, I don't know if I can focus this any better or not. Let's see if I can. Hey, ooh, there we are. No. No, am I passing it? No. No. Can you help me out? More recently, we've been seeing vanadium, supported vanadium used in the SCR reaction, and Mike Amoritas' talk, and then of course Jim Domestic just gave me an introduction to some of the work that we'll be talking about also. Okay, good. Thank you. It's perfect. Okay, solid gas versus heterogeneous reactions. In this case, the vanadium actually gets very involved in everything. If you have a reducing agent, and so I'm not going to talk to you about acidity, and everybody's been talking about acidity in the SCR reaction. I'm going to talk about the ammonia as a reducing agent. It can of course react with adsorbed oxygen, which we know, we get a heterogeneous reaction, but also can react with the lattice oxygen. And if it does so, you can actually bulk reduce the whole material. As the surface gets reduced by removing the oxygen, then actually oxygen can diffuse through the bulk to replenish that, and you can reduce the whole bulk from the outside in. You also can talk about the metal, valence state of the metal, whether in the case of vanadium it's 5 or 4 or 3, and how that can change the absorption properties of the reaction, so we're going to talk about. So we'll look at that. Now, how do we actually look at this in situ? First of all, I'll show you the experimental, and I'll spend a little bit of time. This is a session on catalyst characterization, and because we're introducing a somewhat new technique, I'll spend a little bit more time than I normally would. And we'll talk about infrared emission spectroscopy. And then I'll show you a little bit about vanadium returning with V2O5 reduction. And then again, I'll add NO and NH3. And then we'll talk about conclusions. The mechanism I'm going to be talking about mostly, however, is what happens to the oxide, that part of the mechanism, and not necessarily what happens to the species on the surface. So, of course, they have an influence on that. The type of equipment we used is shown here. We use, on the left-hand side, is this the right thing here? We have, we either put oxygen or NO and ammonia or ethylene we use as a reductant. And we either use a microreactor or use an in situ emission cell. And we use a mass spectrometer on the effluent so we can determine exactly what was happening in, with the interaction with the catalyst here in either of these two configurations. The most unusual way, configuration, was in an emission cell. Now, infrared, you know about infrared. You take a little glow bar and you send it through the sample and you find out how much light is attenuated by the sample. Here, the source of the light is the sample. There is no external heating aside from heating this on a copper block, or actually this is a stainless steel block here, and we actually use a gold mirror on the top here. We take all of the light over approximately 90 degrees and collect it and send this into the optics of the infrared spectrometer, a Fourier transform infrared spectrometer. And you get the same type of information, as you'll see, as if you had done the absorption spectroscopy. This is, we have a little, this is a microreactor, and actually the gas inlet isn't here. We actually bring the gas right above the sample, a small needle that allows the gas to be put right over the sample so we can watch what happens when it interacts with the gas. In emission spectroscopy, and oh boy, now we're having focus problems again. In absorption, when you hit a sample with light, you absorb over a given quanta. The same thing will happen if normally the sample is hot enough and it will actually emit the same quantity of light that it had absorbed. The same frequency associated with that. It's a kind of a hard experiment. You have to get exactly the right thickness. I didn't touch anything. It's magic. And it's great. Zap! No. I'm sorry. In emission spectroscopy, one thing you have to worry about in general is after the light is emitted by a sample, it can be reabsorbed, both by the sample itself and also by things on the surface or things in the gas phase. So you have to have the thickness just right in order to be able to get a proper spectrum, because otherwise it will reabsorb the same energy that it's putting out. And you can actually get inversion bands and bands that go in the wrong direction. So we are actually using a very, very thin film of vanadium on a gold gold substrate here, and the gold, of course, because we don't want to be totally reflected and inert in our sample. The infrared spectra of the various species are shown here, and you'll see that we're down in frequency fairly a lot lower than the infrared that Domestic talked about before when you're looking at these sort of species. Vanadium-5 is shown here, and you'll see a large absorption band, approximately around 1,000 wave numbers, or microns for those of you in the physics community that are shown here. As we reduce the material to a V2O4, this band will disappear, and another band will appear very close to 900, between 8 and 900 centimeters to the -1. And then as we go even further down to V2O3, that band now disappears. So actually, if we can monitor these bands here, specifically the one around 1,000 and the one around 900, we can actually watch as we bulk reduce the material from 5 to 4 and down to 3. The space groups for the various species are shown here, and we will watch them occur, but only by watching the infrared. This is, and I've kind of switched things around here. This is the spectra we see, the emission spectra we see for V2O5. We put this in a, we're exposing this to ethylene, and we're watching here at 0 or 1 times 0 is the first one here, then at 1 hour, 2 hours, and 3 hours. And as we see that, we see the total reduction down to V2O3. in this material. You'll see some in intermediates. You see some sort of band of absorption here, again, around 900 to 800. That is the V2O4 species as it grows in, and we lose the V2O5 species here. Here, I just integrated those various species, the V2O5 band, which is the one in between 900 and 970 and 1030 wave numbers. We see that disappearing in all these cases, and this is a function of temperature, 300 degrees, 325, and 350. Very quickly, at 350 degrees in ethylene, this disappears. This is the V plus 4 band, the one between 870 and 930. And that grows in, again, as a function of temperature, very slowly at 300, much more quickly at 325, and at 350 very, very quickly. And it actually goes in, and then it disappears in each of these cases as we go past the V2O5 species, the V2O4, and then to the V2O3 species in this experiment. In this case, we're looking at ammonia reduction. And again, now this is just exposure of ammonia, approximately the same time frame as before. The initial spectra shown down here. And we're down here to, I think it's about 10 hours. We finally go all the way over to the V2O3. And in the intermediate state, you'll see this band growing in, which we attribute to the V2O4 species, the vanadium-4 species in this. So the V2O5 disappears, and the V2O4 comes in and then disappears in this spectra here. And again, we're showing this for a reduction by ammonia and helium, 2.5%. And we're just showing here the 300 and the 250 degrees. We see a much more rapid reduction at 300 and a fairly slow tail off at 250. This is the V2, the vanadium plus 5 band. And the vanadium 4 band, in this case, goes up and comes down at 300 degrees. And then it actually gets fairly large and stays up there at 250 degrees in ammonia. Ammonia is not as efficient a reductant as is the ethylene that we used in the first case. So we actually can stabilize a not totally reduced sample in this case. What we're doing here is we're actually seeing the vanadium 5 converted to vanadium 4, and we actually convert as that kind of shrinking in the sample. These are not high surface area materials. They're powders, and these are not supported also, I'll remind you again. And as we convert from the 4, then we can convert to the 3. The question is, what is the rate controlling step in this process, and how does this occur? And to do that, we can plot out the data. Here, the vanadium 5 band, and this is actually the reoxidation of the material using oxygen. We can go backwards and forwards at various temperatures. Again, the low temperatures down here, and then we go faster and faster as we increase the temperature, again up to 350 degrees in the top here. And the vanadium 4 band, again, disappears in these cases as we reoxidize the material all the way back to the vanadium 5 in full oxidation. If we plot out the band intensities as a function of the square root of time, we find a fairly linear picture of both the reduction and, as we'll see in a second, the reoxidation. This is very indicative of a diffusion-controlled mechanism, where it's the diffusion, but it's the diffusion of the oxygen, lattice diffusion of the oxygen to the surface that allows us to do this. This shows both the activation energy for the oxidation and the activation energy for the reduction, and we get approximately for these two processes somewhere around 180 kilojoules per mole, which might surprise you. That's a very large number, and why would you get something that's that large for a diffusion process? To understand that, we have to go to the people that work on diffusion and lattice vacancies that tell us that actually the energy, that's approximately the energy you would get from moving an oxygen atom from one spot to another through the lattice, and you get approximately 256 kilojoules per mole for that heat difference, and the activation energy would be approximately what we're getting, around 150 kilojoules per mole, not kilocalories, I'm sorry. So that's approximately what's going on. Now what we're going to look at is the combination of ammonia and NO. Now, ammonia, I pointed out, was a reductant. NO will reoxidize this sample. If we reduced it in NH3 and put NO back on there, it will slowly go back to vanadium plus 5 species. It takes a long time to do that. And I know I'm not talking about acid-base chemistry here, I'm talking about redox chemistry, and that's what we see. Indeed, with the ammonia here, we see this vanadium 5 disappearing, and we also have the NO here, and we also see the vanadium 4 seems to grow in and be the dominant form in here. If we go further, even at stoichiometry, the net result of ammonia and NO is a reducing atmosphere. The NO is not a very efficient reoxidizing species, but we can watch it. Again, it's much more slowly being reduced with the NO present, but it will slowly reduce all the way down. Here I'm showing you here the integrated band intensities, here from vanadium 5, vanadium 4. These are temperatures of 315, I believe, and 300 and 315 degrees, the differences between the vanadium 5 and the vanadium 4 under reaction conditions. In all cases, we see the vanadium 4 being a dominant species here as we go along in these examples. The activation energy for the process is approximately 206 kilojoules per mole, and again, that's having to take the initial rates because what's happening is that we're actually getting a switch in mechanisms. So this is not a supported system, so as we reduce the system, the products that we produce are changing. To do that, and I'll be very simplistic in doing that, here's the conversion of the yield of nitrogen, which is the desired reaction. We see the NH3 conversion being high at first and decreasing. We see building up of the N2O, which is a byproduct, something we don't necessarily want, and the conversion of NO is going down, and it levels off here. And again, I must point out, this is not a supported system, and we actually are over-reducing it far more than we need. To understand what's happening here, we can just look at simplistically a desired reaction to produce nitrogen, a less desired reaction to produce N2O, and then the bulk reduction itself, where we're going all the way down from the V2O5 eventually down to the V2O3, and we can just look at these three processes. Process 1, which is what we want to produce nitrogen, process 2 to produce N2O, and process 3, which is the one that allows us, or that reduces the whole solid. If we do that, here is the desired reaction going down over the process, and again, this is over a period of time, 5 hours in this case here. The N2O production increases. It starts out at 0. It is not a byproduct of the initial reaction. It occurs on a partially reduced oxide, and this is the bulk reduction of the oxide that finally is complete by the time we have 5 hours of reaction on this particular sample. We also conclude that NO is absorbing directly on the catalyst when it becomes reduced, not in the fresh catalyst. So the picture such as this is very proper for a fresh vanadium plus 5 catalyst, but we see direct evidence that NO is absorbing on a reduced system, and that may be, that's what we believe gives rise to the N2O formation, which grows in with the reduction of the bulk in this case. That's maybe where that's happening here. So for the absorbed NO, we believe that we're getting some sort of NO-NH2 reaction that gives rise to the N2O, and it's on a reduced vanadium that this reaction occurs that we're seeing here. Okay, so let me conclude. So we'll have some time for some talks and get you back in. The emission infrared can monitor the changes in the oxidation state near the surface. It is a surface-sensitive technique because the bulk, when it emits radiation, will be reabsorbed by the surface. So you are sensitive to the surface, and this will effectively enable us to get that information. Bulk reduction, oxidation reduction occurs sequentially from 5 to 4 to 3. We have direct evidence for that, 4 being the intermediate for the total reduction. The N2 production by the heterogeneous reaction generally decreases as the reduction proceeds, and the N2O production first increases and then decreases a little bit because we believe that the vanadium-4 species gives rise to the intermediate production of the N2O by the absorption of NO on the surface. And both the selectivity and the activity change probably resulting from the change in this mechanism of the NO adsorption during this bulk reduction. Now, how much this pertains to the supported system on titania, we did not study that system directly, and I will have to leave that to your own conclusions that you can draw. Thank you very much.
Thank you very much for your communication and leading time for discussion. We have time for several questions. Those who want to ask questions, line up to the microphone, please. Line up to the microphone.
Volta, CNRS France. You didn't mention suboxide vanadium between V2O5 and V2O4, like V6 or 13. And this is very important in terms of structure sensitivity and shear structure for catalysis purposes. Can you comment on this, please?
One thing I can comment on, we did not totally reduce this sample. What we did both vanadium and oxygen characterization of this system. The net result, even when it was all vanadium-3 on the surfaces that we could detect, was an average of about a vanadium +4. That is in terms of stoichiometry of oxygen. We did not see any evidence, but we did not have any spectra for any of the suboxides. If we had more information, we might have looked for them. We did not, even in this case, at 300 degrees, we did not go below a net reduction to approximately V+4, though the surface was V+3, and we believe that the only way to do that is that we actually had that V+5 in the internal portion of the sample.
Curt, I have one comment concerning the kinetics of the reduction, namely, you use simple parabolic low, whereas this is a typical shrinking sphere model, which is described by a type of Yandor equation where you have to introduce the decreasing cross-section of the reaction. If you do that, you will probably get much lower activation energies, which will be more compatible with diffusion. This is the first point. Second point is the question, to what extent you see all elementary oscillators? Because you are assuming that your intensity of emitted radiation is proportional to the number of elementary oscillators. Now, the oscillators which are excited inside the sample will give a smaller contribution to your emission than those which are sitting at the surface. To which extent this can be sorted out?
It's a very good question. I wish we could sort it out. We did not, going into this, we did not even know how surface sensitive this was going to be. But it developed that it was a very surface sensitive technique because we do not see suboxides. Even when the average is vanadium +4, we do not see any evidence for it. When it's totally reduced on the surface to vanadium +3, that's what we see. We have not seen either good theoretical work that will describe what happens when you're emitting through from one through the other. That we don't have a good handle for that, and that's one of the weaknesses that we have in interpreting this. So I had to just use an integrated intensity, and I admit that's a poor way to do it, but it's the only thing we had in hand at the time.
Toscan, Ohio State University. Some of our own studies with bulk vanadium pentoxide crystals indicate a high level of anisotropy for these crystals. For example, when you consider oxygen diffusion, the diffusion parallel to the 010 plane seems to be much faster than diffusion in perpendicular to these layers. Have you observed anything in your model? You seem to indicate a multidimensional diffusion which is equal in all directions. Have you considered a difference in the diffusion rates?
No, we didn't. And we did not have the samples that are prepared with different morphologies that would be ideal for exactly what you're saying. If you could get crystals that had different planes exposed, that would be a very interesting study. We did not do that. This is just bulk. You buy it, it's powdered material. I believe it's crystalline, but it's microcrystalline domains more than single crystal materials. You'd have to be very careful to do that. That would be a very interesting question.
Actually, some of our work we have done that fairly extensively, and there's a lot of structural specificity, especially in regard to ammonia adsorption, how ammonia is adsorbed, and how it is reducing the bulk whether you start from the 0, 1, 0 plane versus from the side plane, there's very fundamental differences.
That's very nice. I'm sorry we didn't do the study that would enable us to contribute to that, but I certainly believe that's the case.
Any other question?
Here's one over here.
Yeah, could you go to the microphone?
I think I can talk loud enough. Can you reoxidize the vanadium?
Yes.
All the stuff you showed was a one-shot experiment
No.
with fresh powder, or
We went back and forth.
It's completely reversible.
Completely reversible. You can just turn on the oxygen. You can turn on NO, and it'll do it. It takes you a long time. If you don't want to wait that long, you turn on oxygen, it'll do it immediately. NO will slowly reoxidize the material. And obviously, higher in temperature, the better off you go. And then these samples you just oxidize and reduce them, oxidize and reduce them. You can do it any number of times, totally reversibly in these cases.
Any other question?